Okay, so I just clicked on that link from My Lambda, where here it says Tool and Canvas to get to this page. And you see I have a few more options probably than you, for the reason that I taught a different course last unit. But you'll see this data wrangling and storytelling, and you'll know that this is the unit that we'll be focused on because it says DS1.1 DSPT9. So that's us, and the 1.1 stands for, sorry, let me just move the Slack out of the way. The 1.1 stands for Unit 1 Sprint 1. So Module 1 is today, and this will cover the next, I think, 2 weeks. And so I've clicked on that, and I've taking a look at the module. So I'm actually in the instructor view, so yours will look slightly different. So I'm going to change this to student view, so it'll match what you see on your screen. And you'll see I've got home on the left-hand side and modules on the left-hand side. And if I click on modules, it's going to give me the 4 modules that are part of this sprint. And today, we'll be focused on this module 1. So I'm going to go back home for a second, just to show you the other links here. So we've got 2 links for your module retrospective and sprint retrospective forms. And then we have an overview about what this unit is focused on. And then we have explanations about each of the sprints, or sorry, each of the modules in this sprint. So today we're going to be focused on exploratory data analysis. Now, loading data is fundamental. Getting it in the right shape and format for analysis is very fundamental, but it can be a really challenging part of data science, and it's a very important part of it. But you'll find that the more and more you practice these things, the faster and faster they come. These are some of the same tasks that you'll be doing every single time you approach a data science problem. So today we're going to be focused on exploratory data analysis. And the components of this lecture will be reading in a data set and visualizing that data set. There's a couple things that we'll cover first about accessing the actual lecture materials, but that's going to be the focus as far as our lecture. So if I click on this link, exploratory data analysis, you'll see the main goals of what we're trying to learn today. So how to load a data set from a URL, how to load a data set from a local file, using basic Panda functions for exploratory data analysis and generating basic visualizations. You'll also notice that there are some Module 1 class recordings. And these recordings are from previous lectures on the same material. Now, you may notice that it's a little bit different because I don't think that Canvas was used for all of these recordings, but the material will be the same. And if you want to prep for the lesson ahead of time, you can watch these lectures to kind of get a head start on what we're going to be covering in the lecture. So, for instance, let me go back to the previous page. If I want to see what we'll be covering on Wednesday, I'd click on this Make Features link, and you can see some recordings for Wednesday's class. So this is Canvas, and this is where all the course materials will be located. Also, the modules will be, so each of these modules, let me go back. So I'm in the student view. Let me leave my student view for a second. Under the published courses, you will see the next sprint the Friday before, I believe, the Friday before you start it. So you're not going to see all the sprints for the whole program. You're only going to see the ones the Friday before you start it. So that's why this is probably going to be the only one you see. You may see one for pre-work as well. I'm not sure about where your pre-work materials were located. Okay, let me take a look at our Slack, see if we have any questions. Okay, just about our 5th days. We'll also be using another tool outside of Canvas called GitHub. So let me type in github.com. You may have used GitHub before for a different project, or maybe you've used it for work, or maybe you've explored a little bit about GitHub. Hopefully you've made an account already. GitHub is used for storing code and also sharing code. It's also a method to version code and collaborate between different people on the same code. So imagine if all 50 of us are working on a project, or imagine if all 25 of us are working on a project together. And we need to make sure that we're not stepping on each other's toes with our project. We can keep track of changes in our code, keep track of different versions, and collaborate together. It's also the way that Lambda School stores all the code for the lectures and all the code for the assignments. So that's the reason that we're going over this GitHub. And the way that we access GitHub for Lambda School is by navigating to github.com/Lambda School. And you'll see here that there's 942 repositories. Repositories are just a fancy name for separate, let's call them projects or groups of files. Now, we're not going to be using all 942 of these. The reason that there's so many is because there's a ton of different classes that are taught at Lambda School in a lot of different programs. In addition, there's some archive versions of the same courses. So the way that we'll find the repositories for us is by searching in this Find a Repository section. So the way we find the data science program repositories is by typing DS. And we're in Unit 1. So if I type in Unit 1, Unit -1, then I'll see the different repositories for Unit 1. You can see here it's pulling up Unit 4, Sprint 1. That's not ours. We're interested in this Unit 1, Sprint 1, data wrangling and storytelling. We're on Sprint 1 today, and we'll be here until the end of next week. So this is the one that we'll be focused on. And if I click on this, we'll see a few different things. So we see 4 different folders. We see Module 1, Module 2, Module 3, Module 4. This is for each of the lectures. So today is the first lecture of Unit 1, Sprint 1. So we're going to be focused on exploratory data analysis. So if I click on that folder, then we see 2 files, exploratory data analysis and exploratory data analysis assignment. So this is the assignment that you'll be completing, and this is the blank lecture notebook that we'll be going over today. So the way it works is that there's a blank version of the lecture notebook that you're provided. You can find them by navigating to them in the same way that I just showed you. But during the lecture, I'll be filling it in and doing some live coding for you as well, and I'll provide that completed notebook to you, a link to that completed notebook at the beginning of the lecture, so you can watch me fill it in as I do it. But you can access the notebook that we'll be using for lecture here, and the assignment that you'll be completing after lecture is over, I believe tomorrow. So I'm going to click on this notebook. And GitHub is really just a way to store code. It's not a way to run code. So I'm scrolling through this. There's a lot of text in here, some pictures, and some blank sections of code. Okay, but if I want to actually run some Python code, I have to take this file And this file type you may have noticed is an IPYNB file or an IPython notebook file. So if I want to actually run code for this file, the way that I'll do that is that I have to open it up into something else. And that something else that we'll be using to run code is something called Google Colab, which is the next tool that we'll be using. And I know this may seem overwhelming if you haven't used these tools before, which I'm guessing most haven't. It may seem like we have so many tools. I promise once you get the hang of it, it's really not that hard. You'll be doing it so frequently that it'll just become a habit. So the next step is to go to Google Colab to actually open this file and edit it. So how do we do that? Well, what we'll need to do is go to colab.research.google.com. And this is a service that Google provides to you to allow you to run files, allows you to run Python code essentially, and run Python notebooks. Now, this is Lambda School's copy. And the reason I know that is because in the upper left-hand corner, it says Lambda School / DS Unit 1 Sprint 1. So in order for me to edit it, I have to make my own copy of it. So how do I make my own copy of it? And before I am able to edit it in Colab, I have to make my own copy. And this concept of copying a Python notebook is called forking. So you may have heard forking a repository. If I want to fork a repository, the way I do that is by clicking this fork button. So if I click fork, and I've actually already forked this repository, so it didn't do anything. But you'll when you fork a repository, you'll notice a fork going inside a book, and that's the way that you know that you're forking a repository for the first time. So now, if you notice, I'm no longer on Lambda School's page. I'm on V. Narayanaswamy's page. And it has that same, this is the higher level folder above the exploratory analysis. And you'll notice that underneath it says forked from Lambda School DS Unit 1 Sprint 1, which tells us that this repository was originally from there, and I've simply made a copy of it. So I'm going to go back into that folder, and I'm going to go back to that file. Okay. And now if I want to edit this file in Colab, I'm going to take this address. I'm going to go back to Colab, and I'm going to start over. I'm going to type in colab.research.google.com. And then I'm going to say that, so I can load the file from different places, but in this case, I want to access the file from GitHub. I'm going to paste the link in there. And once I do that, it's going to search for the file in GitHub. You may have to tell Google Colab that you want it to be able to have permission to access GitHub. So there may be that additional step. I've already done that. So if you're not able to access it and it asks you, do you want to give Google access to GitHub? You may have to do that. Say yes, and then once I find the file, I'll click on it, and now I can edit the file in Google Colab. Okay, so now I can actually make some edits. And as a test, why don't we click inside here, and we'll say, maybe I'll add a block of text, and I'll just say, this is my test. And then I'll save a copy in GitHub. Okay, and then I'll say, okay. So I'll look at where it's saving to, DS Unit 1, Sprint 1, Data Wrangling and Storytelling. In that repository, this is the file path. I'll say, okay. And then it pops up with the same, now I'm back in GitHub. And if I look down, you'll see that it saved my code. So this is the method that we access a file in GitHub, fork that repository, fork that file, make a copy into your own GitHub location. You access the file in Colab, make your edits in Colab, and then you can save back to GitHub. There's another option that we have. So and you can talk about this with your TLs, but when you submit assignments, your other option is to save a copy in Drive. And you can just store the file in basically a Google Drive. So if you've used a Google Drive before, it's just Google's cloud to store different files. And you can also share this file by clicking share. And then copying the link and then sharing it with your TL for assignment submissions. Now, there's no expectation that you'll be required to make a copy of the lecture notebook and submit it. The only submissions that you're going to be doing are for the assignments. So if I go back to the assignments quickly, what you'll be doing is accessing this file, this assignment file, opening this in Google Colab, making your edits, and either providing a link to the file in Google Drive or providing a link back to GitHub for your TL to look at. And you may or may not use this pull request. I'll briefly cover it, but once you've made an edit to a file, so let me open this up in Google Colab. So I'll say, it looks like we've got a comment in the chat. Oh, sorry. Okay. So what we'll do is, okay, where was I? So now I've made my edits, and you can see my edits have shown up here. I just added that as the text. Another option that some use to submit assignments is something called a pull request. And the pull request allows whoever owns the repository, so somebody at Lambda School, to see your change. If you click new pull request and then create pull requests, and then let's say Vignesh's pull request. I'll just say test pull request so they know. And then if I, maybe I actually won't be, so won't cause any confusion, but if I click create pull request, then anytime that I make an edit to this file and save it back to GitHub, then Lambda School will be able to see that I've made a change on my file. So few different methods that I wanted to cover. I know this is all new, so it feels a little unfamiliar, but we can make a copy of the file on my drive and edit it there, provide the link. I can also make a copy of the file and provide the link to my GitHub repository, or I can also create a pull request and link my file from GitHub back to the original repository, or repo for short, so that the repository owner can see those edits. So a few different options for assignment submission in linking files back from GitHub to Colab. Okay, so let's maybe take a little bit of time. I think we have some time, so why don't, well, actually, maybe I'll leave that for after the lecture to practice making the assignment submission and making a copy of the notebook. Why don't we go ahead and look at our lecture for today? Okay, so I'm going to go ahead and access our lecture notebook. So we've made a few copies of this. So let me go back to the copy that I'm planning to walk through for today. And I'll share this, this file with everyone after the lecture. So our first step is to load a data set. In this case, this data set will be in CSV format into this Google Colab. Oftentimes you'll be working with CSVs. It's a really common file type. And for this particular data set, we're going to use something called UCI, which is a great source for a lot of different data sets for machine learning. So UCI is University of, I think, California, Irvine provides this service. And if I take a look at, so I've just typed into Google UCI data sets and looked at the first link. You can also just go to this archive.ics.uci.edu/ml/datasets. Easier just to look up UCI data sets. And you'll see that there's 557 different data sets available here. All for different sort of flavors of analysis. Oftentimes, this is a great way to access a data set if you want to practice something in machine learning or explore a new technique. These are all great data sets. We'll be using something called the flags data set. So I'm going to scroll down, click on this flags data set. Okay, and it has some information about the data set. It says, this data file contains details of various nations and their flags. In this file, the fields are separated by spaces, not commas. With this data, you can try things like predicting the religion of a country from its size and the colors of its flags. And it's got different attributes. It says 10 attributes are numeric, and the remainder are either Boolean or nominal valued. And then here's a list of all the attributes. So let's go back to our Google Colab. And let's read in this data set and explore some different facets of it. So first, we have to tell Google Colab that we want this file located over here. So how do we do that? Well, one way to load a file into Colab is by loading it via the URL, which is what we'll be doing here. So if I go to the data folder and I click on flag.data, it'll download the file, or I can look at the path. So if I copy the link address and go back here, I'm going to paste that into this code block. You'll see that this matches the same URL that's already listed here. So what we're doing is we're simply taking that file located at this location, and we're taking the URL of that file and we're saving it to a variable called flag data URL. If I want to run the code block, I can press this little play sign in the corner, and it actually gives me the gives me the shortcut. It says that I can also press Control and Enter at the same time. So hold Control and then click Enter, and it'll also run the code block. There's also this exclamation point curl and then the hyperlink, which just outputs not Python code, but it's going to output that same file. If I were to read it, just open the file in a browser or some sort of text editor. So that's what that exclamation point curl is doing. But main part of this code block that you would want to understand is, how this is working, which is this, that we're specifying the URL and we're making it a string by putting it into quotations. So we're telling Python that it's a word and or a list of characters, and we're saving that string into this variable called flag data URL. Okay, so all we've done so far is saved that flag data URL into a variable name. So the next step is to actually load it into Python, into Colab. So how do we do that? Well, first we'll be doing something called importing. So we're importing a package. And we're going to import the Pandas package. And we're going to say as PD, which is just a common industry abbreviation for Pandas. So import the Pandas package as this abbreviation PD. You could use a different abbreviation, but nobody does. So all the examples you'll see online are usually referencing this PD. And then I'll define something called df, which in data science is called a data frame, which is just a data structure that is very common. Now you can name this variable anything, but we're calling it df. Again, a lot of the examples that you'll see online will use that same abbreviation, df. And then we'll say that df is equal to PD. So we're saying from the pandas library. And then we're asking it to use this read underscore CSV function, which will allow us to read a CSV. And we're saying to read the CSV from our flag data URL location. And you'll also notice that Colab is providing this autofill for us. So flag underscore data underscore URL, it's already an option. I can click on it. Or if I just type flag, and then if I see it pop up and just say tab, then it'll auto-populate for me. Okay, so I'm gonna try Control Enter to see what happens. Nothing's popping up, which actually is a positive thing. That means that the code ran successfully. I didn't get any errors. Okay, but I haven't told Python that I want to view it. So how do I view this data frame? If I want to add a new block of code, I can add code or I can add text. Well, what's the difference between those two things? Well, here you can see all these headings, all the text at the top, all of that is in Python code. So in order to type code, I have to click this little plus code, and a block will appear that will allow me to type code. Now you may have noticed here that this section is green. These letters are green. This is called a comment. So I put this hash mark next to it to indicate that this is not code, and it should just be ignored when we're running the code. So I'm going to say view data as a comment, and let's see what happens when I just put in df. Okay, So I type in DF and I can start to see some data. Pretty big data set, at least for this small window. Maybe not a big data set by other standards, but for this window, it's harder to see. But it says I have 193 rows and 30 columns. Okay. Now, another way to get some information about this data is to type df, and then when I press period, I'll see some different options for different methods that I can run or different attributes about this data set that I can view. So the first thing that I'm going to type is df.shape. Again, it's auto-populating. And notice that I'm seeing the same numbers that I saw before for the size of the data. So I have 193 rows and I have 30 columns. I can also use something called the head. So I'll say df dot, and again, it auto-populates. This gives me the first 5 rows of my data frame. Actually, in this case, it's 4 rows, but it's interpreting the actual first row of my data as a header. We'll talk about that in a second. That's why you see this is bolded, looks a little bit different. I can also specify that I want some other number of rows to show up. So inside df.head, I can put in a number, let's say 10. And that'll output the first 10 rows of my data. Alternatively, I can look at something called the tail, which is just the opposite of the head. So if I say df.tail, it'll give me the last 5 rows of my data set. Now, I looked at the shape of my data set. So I'm going to comment these out. When I looked at the shape of my data set, it said I have 193 rows and 30 columns. But I know that that first row was actually a header. So let me look at it again. That first row was inputted as a header. So it's saying that the header is this country, these numbers. Well, this doesn't look right. It looks like it's following the same structure as the other rows. So the question is, how do I specify that this data set has some column headers? How would I figure that out? Well, there's a few different ways that we can look at Python documentation. One way is to use this question mark, and I'll say pd dot read, and then I can just scroll down, autocomplete with the tab, open parentheses, close parentheses. Notice that Colab is giving us this information about this function. It says read a comma separated values CSV file into data frame. So that's a brief explanation about what it does. And then it has the various arguments that this function takes. It also has some additional information like the parameters, data type, all sorts of information. But instead, I can also just use this question mark pd.read CSV. And I run this, you'll see what pops out on the side, some information about this data set. Or sorry, about this function. An alternative way that I can look at Python documentation is by using this help function. This will give us some more detailed information. And notice here, there's this argument header that says row numbers to use as the column names and the start of the data. Default behavior is to infer the column names. If no names are passed, the behavior is identical to header equals 0, and column names are inferred from the first line of the file. So that's probably what's going on. Now, I know this seems a little bit cumbersome, but reading documentation is an important part of coding, and you'll find that it comes more and more naturally later on. So for instance, maybe instead of looking here, I could also just Google it. So maybe I just say read.csv and Python. Actually, let's say in Pandas. And the first link is to this Pandas read CSV, and it has the actual documentation from Pandas about how this function works. This will be more and more familiar the more and more you do it, but you can see some information like the arguments this function takes and some additional information about what each of those arguments are. Okay, it's 7:45 where you are. Let's take our first break for 5 minutes. I'm going to go ahead and set a timer. Please walk away from the computer. Just relax a little bit. We'll have plenty of time to learn when we come back. All right, back from our break. Now, I'm going to reference the question thread. There are a few questions that I want to talk through. So our first question is, not sure about Repel IT. Maybe one of the TLs can provide an answer to that. Another question, Jay asks, can we make all our imports in one code block, or should we wait to get to the line of code where we use that specific library? So this is a great question, and it kind of hits on, well, what is the purpose of this IPython notebook? Or you may also hear the term Jupyter notebook. Originally, these notebooks were designed for Python. Now they're more general. You can use these Jupyter notebooks for other languages too, like R. But the reason that these tools are these IPython IPYNB files are useful are because we can interact with the data, we can share the data, we can do these sort of lessons where I can do the live coding and you can see the code run. But that's not necessarily how this code would operate in a production environment. So for the purposes of the Python notebook, all right, you may not know ahead of time what imports you need at the beginning. If you're doing exploratory data analysis, you may only realize that halfway through the analysis you need a certain package. And certainly you could scroll back up to the top, insert that package into where the other packages are located and run that statement and come back down, but you don't have to. If this were in a production environment, so in other words, if this was just a Python script, and we were using this code in a production environment, I wouldn't have any of this text, and I might have comments, but I wouldn't have all this markdown text. And probably at the very top, I would list out all the imports at the very top, but there would be no blocks of code, so nothing would be separated into different blocks. That concept wouldn't exist. It would all be in one script. So good question, and it kind of relates to what you're actually using the script for. If it's in a Python notebook, it may be appropriate to leave those imports in. But if it's in a production setting and you're using the code for some production reason, then probably you'd put the imports at the top. Another question is, how do we move the cursor to the end of the statement without using arrow keys? I'm asking because parentheses and brackets are automatically closed. So this may or may not be what you were asking. If it isn't, just let me know. So let's suppose I type in some string here. I'll call it my string. I can automatically close the parentheses by double clicking on that string and typing whatever I want to open and close. So if I just single click the quotation, it'll automatically put that into quotes. If I single click the parenthesis, may have to hold shift. Oops. If I hold shift down and then press the parenthesis, then it'll open and close the parenthesis on that word. So maybe that's what you're asking. If it wasn't, feel free to clarify. But we can automatically close the parentheses that way. Okay, so let's take a look at our data set again. Let's go back. Scroll up to the top. Now the issue we were facing was that the first row of the data was showing up as the header. And we referenced our documentation. And it said that when I use this help PD, yeah, good question. So how are these data sets, the one on the UCI dataset website, generated? I'm not sure on the source of all those data sets. That's a great question. If anybody knows, maybe the TLs, feel free to answer. My guess is it may be a combination of both, because there's so many of them. So if I look at this read CSV in the help function, it says under header, row names to use as the column names. If no names are passed, the behavior is identical to header equals 0, and column names are inferred from the first line of the file. Okay. And let's see if it gives us an option to ignore that. Let's see what happens when I type in data frame is equal to pd.read underscore CSV. And then I say flag data URL. And then I say header. And it gives me an option to set it equal to something. And so here, instead of header equal to infer, I'm going to say header equals none. And then if I take a look at my data set now, here I have to do a capital N because that's a reserved word for the function. Now that first row is ignored as the header, you can see here instead, I've just got some column numbers. So this is correct, but now my next question would be, how do I specify what these column headers are? So obviously these are different attributes. Column 1 seems to be a country, then I have all these other columns. 3 of them seem to be colors, which makes sense because we're talking about a flag, but I need to get some additional information about these columns. So let's see here if it's on my, under flag.names, let's open this up in a new window. Oops. So it doesn't like that it's a name, a .names file. But we have the list of attributes for the data frame. So now the question is, how do I define those names as the header of the data frame? One way to do it is to first define my column names as a list. So I'm going to say column headers equals, then I'm going to say bracket name, landmass. This is all the names in the data set. Zone, area, population, language, religion. No, I don't have these memorized. I just happen to have the list on my other screen. So I'm going to go ahead and paste these in. Okay. And now I've got the list of names saved as this variable column headers. If I were to take a look at that variable, we can see I've got the full list of names saved here into column headers. I can also define it while I'm reading in the CSV, the header, as names is equal to that list. And now when I read it in, that list of names will be populated as the data frame headers. So, when you read in your data sets, you may run into these issues, and you'll probably be using these things fairly frequently. So good to practice them. Okay, now we loaded a data set from a URL, but what happens if we have a data set located on our machine? So another task that you'll be required to do frequently is load a data set like a CSV from a local file. So how do we do that? Now, it's a little bit trickier in this scenario because we're actually not running code on our machine. We're running it on Google. So first, we have to get the file to Google Drive. It's a two-step process. And then we have to read in the file from Google Drive into memory, into our session. So let's take a look at how to do that. So we can, you'll get comfortable kind of Googling this to figure it out. We could literally Google Colab file upload package, and we'll get this back. For the sake of the exercise, I'm going to show you how to do it. We would just say from Google.colab import files. Okay, so we've imported this package, files, and then we will say uploaded is equal to files.upload. So this allows us to upload a file from our machine. So you'll see that it pops up with this choose files. So previously I've already downloaded the flag.data file. So I'm going to go ahead and read it in. Also notice that although we're using read CSV, it's a data file. And if I actually look at the file, you'll notice that although it is saved as a data file, these are all separated by comma. Okay, so now it's saying saving flag.data to flag.data, and it looks like it's 100% done. So now, how do we read it in? Well, it's actually located in our drive. So all we have to do is we have to say data frame is equal to pd.read_csv. And then we specify the name of the data set, flag.data. And we'll say, again, names are equal to our column headers. We already have those saved. Let's run that. Okay, looks like we're good. Let's add another code block and look at the head of the data set. So I'm going to say data frame head, and looks like it read it in okay. So two options for reading in data sets that are very common. Either A, the CSV is located on some URL and you can read it in just by specifying the URL name, or you'll be uploading the file to Google Colab and then importing it that way. So a couple different options. Okay, great. So we've covered, the basics of GitHub, the basics of Google Colab, Canvas, and how to read in data. So we've already accomplished a lot of basic tasks. Now we're going to jump into something called exploratory data analysis. So what is exploratory data analysis? Well, exploratory data analysis is the process of doing some sort of initial investigations on our data. So we're trying to identify some patterns, maybe some anomalies, understand our data at a basic level, look at some summary statistics, maybe build some visualizations, just get a feel for what our data set is structured like. This is often one of the first things that you're doing. So you read in the data set, number one, and then number two is you try to make sense of the data. So what are the averages of some columns? How many unique values does each column have? Let's throw some of these things on a plot and look how the different variables are distributed. Do I have numeric variables, categorical variables? All those types of things are considered exploratory data analysis. So there's a few different functions that you'll get familiar with. I don't think we're going to look at every single one of these. We may actually, but I've listed them here just for your reference. So the shape we already looked at, head, and then we'll look at some of these others as well. So what are the data types in our data frame? Let's get a description of our data set, look at the different counts of each of the columns and each of the unique values, etc. So let's go through some of these. So let's experiment with some of these. Now we're going to jump to a different data set. So we're going to use this adult data set. Let's look at what this one's about. So it says here we've got, this is from the 1994 census database, which is also a great data source. So the US Census data it's amazing how much information they have. And they actually don't collect it just every 10 years. There's some additional data that the US Census collects more frequently. The 10-year census is the most comprehensive, but there's tons of data that you can pull from public records. The Federal Reserve has tons of data. A lot of the public agencies have public data and APIs available, which you'll be covering later on in your course, I think. But tons of data sources available publicly that you can pull from. UCSI is just one of them. It's very, very good, but there's other ones that you can look at as well. So here it says a set of reasonably clean records was attracted using the following conditions. So it looks like they had to have some conditions in the 1994 census database. And it looks like the design of this data set was for a prediction task to determine whether a person makes over $50,000. And we've got all these different attributes: age, work class, education, marital status, occupation, relationship, race, sex, capital gain, capital loss, hours per week that the person's working. So let's open up this data set and take a look at what's going on. So we will use the similar formatting from before. So we will say adult, let's call it adult data is equal to, and then we'll list this URL. Okay. And it's actually in the extension is, I think it's a, let me just double check. Okay, so it's located at /adult and then adult.data. So /adult.data. Okay, so we've saved the URL as a variable. Now let's read in the data in the same way that we read in the data previously. I'm going to add a new code block just so it's clear. And I'm going to say that the data frame, so using the same name, I could save it as df2 if I want to say both of them, but I'm just going to overwrite it and say this is data frame as well. We'll say that data frame is equal to pd.read, again, CSV, adult data, And then I haven't specified my names. Why don't I do that as well? I'm going to move this down and then run my headers first. Now you can run this all out of order, but it is good practice to kind of keep them in sequential order just so you can keep track of the different steps that you're taking. Otherwise it can get a little bit confusing quickly. So I'm going to say my column headers are equal to my age, and I'll spare you from having to watch me type each single one of these out, and I'll paste the rest of the values in. Okay, so my column headers are equal to this list of columns. And then what do I add here? I'm going to add headers. I'm going to add names equals column headers. And I'm going to run this first with Control Enter. And then I'll run this as well. Let's add at the bottom of this a df.head so we can see our data set. Okay. It didn't like something. What didn't it like? Looks like I didn't read it in properly. Let's take a look at my code. Okay, so I've used the wrong URL. What's interesting is it actually read in something from the web page. Okay, so I need to use a slightly different URL. So that's the description of the data set, but it doesn't actually have the file. So I'll run this, then I'll run this, then I'll run the next line of code to look at the head of the data set. Let's take a look at this data. Okay, so we've got age in column 1, work class. I'm actually not sure what this is. Maybe somebody knows. Let's take a look. It's a continuous variable. Maybe somebody can tell us in the questions, what is this variable? Any ideas? FNLWGT. We've got education number, so the years of education, marital status, occupation, relationship, race, sex, capital gain and loss, working hours, native country, and income. Let's also look at the tail. Let's look at the end of our data set. Okay, I don't see anything totally different here, so maybe it's not in any sort of special order. If I want some summary statistics about my data set, so let me just say, let me add some comments here. Read in CSV, look at head and tail of data set. If I want some summary statistics about my data set, I can use this describe function, which is a really useful function in Pandas. And what we're going to say is df describe, and it'll give us back a description of each of the columns. Now, anybody notice anything? Why is it not listing all of my columns? What is it excluding from here? Any ideas? So I've got the count, the mean, standard deviation, the minimum value. Okay, And looks like we've got some explanations about what this variable means. So I'm curious. The continuous variable represents final weight, which is the number of units in the target population that the responding unit represents. Okay. Not sure I actually understand their description. Andy says, in other words, this is the number of people the census believes the entry represents. Okay, that makes sense. Estimated people each row of data represents. Okay, interesting. I did not know that. Also, Jay says that all the data is numeric, but clearly here I have some qualitative information. I have some categorical variables. So the way this describe function works is that it's only going to include the numeric data unless I specify otherwise. So how do I specify otherwise? Well, I have a couple other flavors of this describe function. I can say describe, and I can say, actually, let me just leave this in here. So when I click inside the function, there's a few options it's listing for different parameters that I can add to the function. Percentiles equal none, include equal none, and exclude equals none. Now, it already has those values none in there, which means that's the default values, but I can also specify something else. So instead of none, if I say exclude number, okay, exclude equals number, then it'll exclude the numbers and give me back all the categorical variables. If I want everything, then I can say include, and I can say all. This will give me information about every single one of the columns. I'm going to list those different options in here so you can play around with them. But it's a good idea just to read the documentation for the functions to see what options exist. So I'm going to put in df describe, which is one option, the most basic, and then we'll do df describe, and then we'll put in exclude number. Okay, few different options for describe. So I'm going to just look at some of the numeric columns, and you'll notice that the code block is only outputting the last line of code that has some output. So in our categorical variables, we've got okay, some of these only have a low number of unique values. Some of them have, look at this, native country, 42 unique values. So I guess that means there's 42 native countries represented. The most frequent is the United States, which is probably expected. This is U.S. Census data. Under education, the most frequent is high school grad. Okay, so some interesting information here. I might also be interested in what types of data I have. So I'm going to put in here, describe my data set. And then underneath this, let's get some additional information, try some of these other functions that we can use from Pandas for exploratory analysis. So let's use, if I want to get the types of data that are in specific columns, then I can use dtypes. So it lists my column out, and it's giving me the different types of each of these columns. Which aligns with what we saw in the previous include or exclude numbers. Now, if I say df is null, which is one of the other functions that was listed, first let me just run df. If I just run df, it's going to give me back all these values. Now, if I say is null, it's going to output what? It's going to output a logical vector in each of these columns, indicating whether or not the value is null. Any ideas how I would figure out the number of nulls? Anybody guess what might be a method to figure out how many nulls I have? Yeah, the sum, exactly. So here in Python, the ones are treated as ones, and the trues are treated as ones, and the falses are treated as zeros. So if I just sum up everything in the data frame, then it'll give me the sum of the null values. Well, I don't have any nulls, so what might I do to maybe figure out if I actually have null values or not? I'm going to use something called, the point that I'm trying to illustrate here is just that sometimes it looks like you don't have nulls, but it's tricky because different data sets can represent missing data in different ways. In this scenario, it looks like I have no null values, but actually that may not be the case. So let me just type in here what I'm doing. So count the number of nulls, and then let's say identify nulls. And one way to do that is by looking at the unique values in each of the columns. So for instance, if I want to look at the unique columns in native country, I can use something called value counts. Value counts gives me the number of times a specific value is showing up in a column. So does anybody notice anything here? What might be our missing values? The question mark, exactly. So now the question is, how do I replace question mark with some sort of missing value indicator? So to do that, I have to replace the values in the data frame with something else when they are a question mark. So to do that, I can use df replace, which is the pandas function to replace things. And it's giving us a couple things. It's saying to replace, value, in place, limit, regex, method. So this is actually a pretty powerful tool. There's a lot of different ways to replace values. In this scenario, what we're going to be replacing is we're going to say that we want to replace let's see. I want to replace my question mark with NaN. So first, I'll say NP-NaN, which is the pandas way of saying missing value. Actually, first, let me, so I've got to import this package, and actually notice that NumPy already, it all auto-populates as NP because that's the sort of standard. So I'll import this so I can work with the NaN values, and then I will use this to indicate that I want to replace the question marks with NaNs. What am I missing from here? Trying to use some, correct. Should it be native country replace question mark NaN? We could do that as well for that specific column. Let's see. Okay, let's see if this is replacing our NaNs let's just try something quickly. So I'm going to say I'm creating a new data frame 2, and then I'm replacing all question marks with NANs. So let me run this. Okay, it ran okay. And then now let me check the is null sum. Maybe it's space question mark. Let's see if this is correct. Oh, this is DF2, that's why. Correct? No. Okay, so it was space question mark in that column. So now when I take the sum of the null values, you'll see that it has 1836, 1843, and 583 null values. So the point of this exercise is really just to illustrate that sometimes even when there's something populated in the field, there can be some kind of idiosyncratic ways that nulls are indicated in the data set. Sometimes it's even 0, which can be extremely confusing, but sometimes they'll just use some sort of placeholder to indicate that there's a missing value. In this case, it's actually space question mark that needs to be replaced. Okay, so I'm actually going to overwrite the original data set. So I'll say df is equal to df replace question mark np.nan. Another useful variation of value counts is to do something called value counts normalize. So what I'm going to copy and paste this same function, but instead inside value counts, I'm going to specify normalize is equal to true. Any idea what's going on when I've normalized the data? Notice that the relative frequency, the relative size of these numbers is approximately the same. So this was the first version. United States is very large. Second one, we have some decimals. So it's a percent of occurrence. And let's go ahead and try to actually contain all the conversation within the question thread. That way it's easy after the fact, after the lecture's over, it'll be easy for everyone to follow along if they want to reference back the questions. But sometimes I miss things if they're not in that question thread. I've done that too many times. Sometimes I even miss things when it is in the question thread. So better to just keep it there. For your own sake. So it's doing the percent of the occurrence. So that's what this normalized true does. So this can be particularly useful as well. I'm going to comment this in. I'll say show percent of occurrence. Okay, great. Let's see, maybe there's some other useful functions we can look at, but I'd encourage you to explore some of them as well on your own. So I think this is good. I think this kind of captures the most of the useful exploratory analysis functions in Pandas. The next section is going to be on data visualization, and before we do that, we will take our next 5-minute break. So step away from your computer, relax a little, and I'll see you soon. Not 10 minutes, 5 minutes. All right, DSPT9. We're back at it for the last 25 minutes to cover data visualizations with pandas. And let's take a look at these. This is actually just basic plotting in Python. Where am I? Where's my, oh, here. Okay. All right. So we're going to look at some basic plots, the line plot, the histogram, the scatter plot, and the density plot. These are some basic plots, but they're actually extremely useful, and you'll probably be using variations of these throughout the program. So great to cover on a first day for sure. So first, let's take a look at this line plot. In order to do the line plot, and in this case, let's do a line plot on age. So if I take a look at the age column, okay, it's a list of numbers essentially, right? Different ages in that column. And if I look at the value counts of that column, then it'll give me the frequency of each of those ages. Value counts. Okay, so we've got from highest frequency to lowest frequency, 36 looks like it's the most frequent age, and the least frequent is 81. Okay, and also looks like another one, 87, also low frequency. And actually, let's sort this. So sort index. Here I'm sorting by the index. And if I want to plot this, doing a basic line plot, all I have to do is just add plot to the end of it. And then this is going to give me a plot of the frequency, okay? So each of those numbers by age. So on the x-axis, we have our age, and on the y-axis, we have each of those numbers that we saw. And it looks like there seems to be some spike at the beginning. It stays relatively stable and starts dropping off, all the way through 90. So looks like a steady decline once we get to about 40 in terms of, and I believe this is actually employment data. So maybe this makes sense. And maybe it actually just reflects another phenomenon of the ages in general in the United States. Okay, so I'm going to deconstruct this for us so we can just see it again in some separate lines in case you'd like to run it. So I'll separate it out with value counts. And then I'll have another version, which is value counts with the sort index. And then I'll have the value counts with the plot. Okay, but while this is useful, this doesn't tell the whole story. And it's not probably the traditional way that we would plot this type of information. When we're looking at frequencies like this, and we're looking at how the frequency varies between different groups of ages, the more common visualization approach is using what's called a histogram. So our histogram is going to bin the values and then give me the frequency within each of those bins. So how do we do a histogram? Well, I specify my column of interest. So I'll say df age, and then I say hist. Okay, but it doesn't really seem to be giving us a good picture. So there's something that I can specify in my histograms called the bins. So if I say bins equal to, let's say, 20, it looks a little choppy. So I'm going to keep increasing that until I get to what looks like a good number. When I have this spiking, it's an indication that I could probably change the number, increase it to get a better representation of my data. And it looks like this 70 is doing a decent job. So it's a lot more smoothed, and those bins look like an appropriate number to represent the data. It actually looks pretty similar to the line plot. But the difference here is that um, with the line plot, it's more jagged because there may not be as many people in each of the specific age ranges, probably too granular. So I'm specifying bins equal to 72, and it looks like there's some sort of spike at the beginning. Large number of people in this age range, looks relatively stable with a slow climb, and then starts steadily declining through 90. Another visualization I can use is a scatter plot. Now, a scatter plot's useful for showing relationships between multiple variables, generally two variables, and it's just giving us a point that represents where two pieces of data lie. So, what is the relationship, let's say, between age? So, let's use our same variable that we used before. We'll say plot a scatter plot, and then here I have to specify two columns. So I'll say age, and then let's say I want to see the relationship between age and the hours somebody works, which is the column hours per week. And I would expect, maybe it seems like people work more as they age. Maybe not. I don't know. It looks like actually there's not really a clear relationship here. It seems like across the board, it's sort of spread out, but it seems like there's some outliers on both ends. For instance, it seems like there's a gap between 80-ish, and then a handful of people working at 90. And also, there seems to be a group of people that are separated from the rest that are working a lot, 100 hours a week. So it doesn't look like there's a clear relationship here, but the scatter plot is useful to show if there's any sort of natural relationship between our data. That type of information is useful for when we get to our, when you talk in your next unit, when you talk about predictive modeling, what type of model you might use. So if this was a straight line, I might use a linear model. Um, but here we don't see any sort of clear relationship. But you could try a couple other variables and see if there's some sort of natural relationship here. Another option for plotting is what's called a kernel density estimate. So the kernel density estimate, similar to the histogram, but it's going to smooth it out for us. So remember that issue we had with the bins? Well, if I use a density function, oops. If I use a density function, it's normalizing it, so it's actually giving me a probability distribution, and then but it's essentially the same as the histogram, smoothed out over the interval, and then normalized so that it's a probability distribution. So I can see, okay, well, what is the probability that my age falls between two values? That's what this concept does. So let's actually compare that to the histogram. That'd be interesting. So I'll say df age, and then I'll use the histogram function. I'll set my bins equal to 72 again. So it looks similar. I mean, it's starting. What's interesting about the density function is that it's a continuous distribution. So, or sorry, it extends in both directions. In theory, so it's going all the way to -20 and past 120, which doesn't even exist in our data set, but it's estimating what the probability distribution would look like. So those values don't actually exist, but you can see that the shape is pretty similar. It's kind of got a maximum here, and then that naturally goes down, drops off hard at the end, the starting point, because people can't, I guess, work before a certain point, or data isn't collected before a certain point. And you can see that same relationship on our kernel density estimate. We can also use cross tabulations and plot cross tabulations. So let's look at our cross tabulations and understand what this does. So cross tabulations are useful for understanding two categorical variables and the frequency of those combinations of categorical variables. So for instance, here, if I say pd.crosstab, which is how I generate a cross tabulation, and I say on one axis, give me the education, and let's say on the other axis, can you combine graph types? You can combine graph types. That's actually a great. So I also will do office hours twice a week if that wasn't mentioned to you. I think we can plan to do office hours at, let's see, so plan to do office hours at 8 o'clock Tuesday, and so it'll be alternating. So depending on if it's an AB week, it'll be the day that's not the lecture. So if we have class on Tuesday, Thursday, then I'll do office hours on that Wednesday. If we have class on Monday, Wednesday, then I'll do office hours on Tuesday, Thursday. We can definitely talk about that during office hours. That'd be a nice topic, combining graph types. So PD cross tab, we'll look at the education, and then we'll also look at the sex and look at the relationship here. So this is going to give us the combination between these two things. So on one axis we have sex, and the other axis we have education. So it's going to tell us, okay, how many males do we have in 10th education, which I'm assuming is 10th grade? How many females do we have in 10th? So we have 638 males, 295 females represented. And if we look at, let's say, the ninth year of education, male is 370, female is 144. And it actually looks like across the board, male is higher here. So it looks like there's some sort of imbalance in the data set. So maybe we would do some research and see, okay, is this some sort of sampling that was done intentionally, or does this represent anything significant? But in any case, it looks like the male values here is higher than the female value for these categories. Looks like down the line, which sort of maybe not expected. We'd be curious about why there seems to be that relationship across the board. So if we want to plot some of this data, the way that we might do that is, well, we have two categories here, and then we have another category that we may also want to plot. So within one category, sex, we have two options, and then within education, we have numerous categories. So how would we represent this in a plot? Okay, so let me save this cross tabulation, and we'll call it our table data frame. And if I want to just output that, I'll just say table. And then it'll output our table for us. And if I want to plot this, then I'll just say table and then just use the basic plot function. And it's going to plot a line plot for us. So what it looks like is that both of these spike at the same time, which is interesting. Maybe there's a positive relationship with education and the frequency of whatever event I'm looking at. Is there a difference between male and female? Well, it does actually confirm what we saw, which is that there's more male values, but for some reason it's spiking in these two categories. So that's kind of unusual. I don't know what to make of that. It looks like it separates significantly at 2 points in the data set. And then comes back together, spikes again, and then comes back together. So what we might do, a line plot often is used for representing time series data. It's probably not going to be the most intuitive to represent categories like this because although there's probably some sequential aspect to the education, it seems like maybe this would be nice to see in a different format. So what are some of those different formats? I'm going to look at a bar chart. So if I and I can actually do this programmatically. I don't have to specify the table as a separate data frame. So let's suppose I want to do two other columns. In this case, I'll do the same columns, but you can swap them out this way. So I'll say cross tab, and then I'll say DF, education, and then DF, sex. And then I can specify the plot. So here I haven't yet specified the plot, but if I specify inside the plot function that the kind of plot I want is a bar chart, then I get some side-by-side comparisons between male and female for each of those education categories. So a little bit easier to see what's going on. This is one style of bar chart. Another style of bar chart is to do what's called a stacked bar chart. So instead of side by side, so I'll take this same bar chart, and instead of putting them side by side, I'll stack them. So I'll say kind equals bar, and I'll say stacked equals true. Okay, and now once these are stacked, maybe this helps, maybe this doesn't. I think in this case, actually, the side by side is more helpful because it's a comparative analysis. But the reason that the stacked is useful is it tells us the overall frequency for each of those categories. So if I'm interested in that and I want to see the composition of each of the categories, I can still get a sense of that with the stacked. But then I also know the total for each of those education categories. So a couple different options for plotting that we walked through. And let's just briefly talk through a summary of everything that we went through. So as far as visualization and visualization is concerned, these are some of the most basics and important types of visualization. So you'll probably be using these frequently. And for your assignment, feel free to just take this code and kind of swap in and swap out columns and see how things change. Remember that, so this cross tabulation is particularly useful for categorical variables. This becomes less useful when I have numeric variables because there's so many unique values here. So imagine that if I have some continuous variable and I try to do this cross tabulation, this isn't going to be as relevant. So cross tabulation is generally for categorical variables. In terms of what we reviewed today, so we went through a lot, right? This is week one, lecture one. So we're trying to keep it intentionally easy win, but every single lecture we're going to be building and building and building. And I think you'll be really, really surprised how much you'll be able to accomplish in this first unit. we're starting with some basics with data manipulation and data visualization, but by the end, we'll be touching on linear algebra and hypothesis testing and all these really interesting topics in data science that are more sort of focused on the statistics and the math and less focused on the coding, but we're learning both in tandem. So it'll be, I think, a great way to learn more about Python if you don't already know much. And it'll also be a great way to learn and learn some concepts in math and statistics if you don't know those. When you learn them in parallel, I think it makes it a lot more fun because you can experiment with the techniques that you learn in math and statistics very quickly if you know how to do it with a programming language. So a lot of new things the first week. We've got a new course. We've talked about a new schedule. We've got a new community. So the people that you're seeing on the video will be, your classmates for a while. We're talking about some new tools: Canvas, GitHub, Slack. Maybe you've used some, maybe you haven't. New processes and new content. So content is just one aspect of this. So if the first week feels overwhelming, that's okay. And I think there's some positivity there. Oftentimes, some of the best things to learn take some work, and if it feels unfamiliar to you or kind of overwhelming, totally normal. I remember the first programming language I learned, and when I first learned statistics for data science, it felt so overwhelming. But it just takes repetition. So just stick with the course material and work on the assignment. And I think you'll be really satisfied with your progress. So your assignment, it says for this afternoon, but obviously it's not afternoon, I don't think, for anybody on the Zoom call. If it is, we've got a lot of time zone represented. But your assignment is to pick another data set from this machine learning repository, UCI. It's intentionally open-ended and a little bit vague because that's what a data exploratory analysis is about. It is open-ended. So experiment with all the functions we talked through, read in the data set, try the different visualizations, see what works, see what doesn't work. Explore other data visualization functions as well. Look at other options. Get in the habit of Googling things, looking at the documentation. That'll carry you really far. Like all languages, they're meant to be practiced, so you have to use them in order to learn them. And I think that's about it. So I think we can go ahead and end for the night for the lecture. Looks like Ethan may be typing. I thought I saw him typing something into the Slack channel.